All right, let's talk about something that sounds like it's been pulled right out of a sci-fi movie. A sensor you can literally paint onto a surface. A sensor that can survive environments so hostile, they'd pretty much destroy anything else we could build. So where on Earth would we even need a thing like that?
Just think about that for a second. To build safer, more efficient machines, we need data. We have to know exactly how much stress or strain a part is under. But how do you actually get that data from the inside of a jet engine or from the skin of a hypersonic vehicle, where the temperatures are just absolutely scorching?
And that's the core problem, right? The delicate instruments we count on for those super precise measurements, they just can't take the brutal combination of intense heat and physical stress. Well, until now, that is.
So to really get why this is such a huge deal, we first need to understand the fundamental problem that has held engineers back for decades. You see, it's always been this trade-off. On one hand, you've got your traditional metal sensors. They're great, super flexible and really sensitive, but you put them anywhere near high heat or a corrosive environment and they're toast. On the other hand, you have ceramics. They can take the heat no problem, but they're rigid and brittle. If you try to stick one on something that needs to flex, like an aircraft wing, it'll just crack. What researchers really needed was the best of both worlds.
And that is exactly what they've created. The solution is as elegant as it is powerful. They call it alloy paint.
The magic really starts with this material called a medium entropy alloy, or MEA for short. The best way to think of it is like a masterfully blended metallic smoothie. By mixing several different metals, we're talking things like molybdenum, tungsten, and niobium, you create this deliberately jumbled up atomic structure. And that chaos, that disorder at the microscopic level, is the secret sauce. It makes the final material way stronger, more stable, and much more resistant to heat than any of its ingredients on their own.
But, having a superalloy is only half the battle. How do you actually apply it to, say, a complex engine part? This is where the real genius comes in. Researchers figured out how to take this incredibly tough alloy powder and turn it into a printable ink.
And check this out. According to the research in Nature Communications, this ink engineering strategy means you can now directly print or even just handwrite a high-performance sensor onto pretty much anything: glass, plastic, metal, even the really complex curved surface of a wing.
Okay, so how do you paint with a superalloy? You're probably picturing some crazy, complex industrial lab, right? Well, the process is actually surprisingly simple.
It's basically a three-step deal. First, you mix the ink. It's a precise recipe of that MEA powder with some special chemicals to keep it stable. Second, you just spray it onto whatever surface you need to monitor. And third, and this is a huge part of the breakthrough, you just let it air dry. That's it. There's no need for these complicated, super hot baking processes that often limit where and how you can even apply a sensor in the first place.
Okay, so it's easy to put on, but does it actually work? Let's get to the performance data, because this is where things get, honestly, kind of mind-blowing.
Just look at this temperature range. A typical flexible sensor, it might operate from about -40 to 125 degrees Celsius. Not bad, but this new MEA paint sensor, it works from -150 degrees Celsius all the way up to an incredible 1100 degrees. We're talking about a range that covers the freezing cold of deep space to the heat of a literal blast furnace.
Now for sensitivity, this number, it's the gauge factor. Basically, it's a measure of how much the sensor's electrical signal changes when it gets stretched. For most sensors, this number just tanks as things get hotter. But at 300 degrees C, this alloy paint has a gauge factor of over -750. That is an extreme level of sensitivity in a high heat environment where other sensors would be failing or just going completely quiet.
And it can detect incredibly small changes. This number, 0.57 microstrain, means it can register deformations that are absolutely microscopic. So what you're getting is extreme toughness and extreme sensitivity, all in one package.
And the perks just keep on coming. Like we've seen, you can spray it on or even write with it by hand. It sticks to weird, complicated shapes. The performance is super stable and repeatable use after use. And, in a really great nod to sustainability, the expensive alloy powder that's in the ink can even be recycled.
So, let's just recap. We have a sensor you can paint on that survives fire and ice.
This isn't just a small step forward. It unlocks entirely new worlds of possibility across so many different fields.
The potential here is just massive. In aerospace, you could get real-time health monitoring on jet engines in hypersonic vehicles while they're operating. In industrial settings, you can embed smart sensors directly into high-temperature manufacturing processes for better control. For robotics, you could build durable soft robots that can operate in incredibly harsh environments. And even in medicine, you could create sensors for medical tools that can survive high-temperature sterilization, no problem.
This technology fundamentally changes what a sensor even is. It's no longer a separate little component you have to add on. It can be an integrated, invisible part of any object. So the final question isn't just about what we can measure, but what we choose to listen to next. A bridge, a wind turbine, a surgical tool. What new stories will they tell us?